Okay, so in the last video we were taking a look at damped oscillations and we got to the point of analyzing underdamped oscillations. Now with underdamped oscillations I want to look at the energetics of that a bit more and specifically introduce a concept called the quality factor. Okay, so we'll start with our mechanical energy. That'll be the kinetic plus the potential. So that is 1/2 mx dot squared plus 1/2 kx squared. Now, since we have a dissipative force here, we're going to be losing energy with time. So the rate at which we'll lose energy, dE dt, well, if we differentiate this, we'll bring down a 2 to cancel the half, gives us mx dot, take the derivative of what's inside, x double dot, and then same deal here, bring down the 2, cancels the half, gives me kx x dot. So I can pull out an x dot from this anyway. So it'll be x dot times mx double dot plus kx. Now, this bit right here should be looking a little bit familiar to you. That's 2/3 of our equation of motion. If you recall, our equation of motion was mx double dot plus cx dot plus kx equals 0. So we can rearrange and observe that mx double dot plus kx equals minus cx dot. Well, that's cool. So what we get from that then is dE dt will be equal to, well, we have an x dot already, so then we times that by minus cx dot, we get cx dot squared. So the moral of the story here is the energy that you lose goes as the square of the speed. So that's why, like in cars, for instance, aerodynamics gets so important at higher speeds. Almost all of your energy is being expended into moving the air out of the way. Now, at lower speeds, it gets lost to rolling friction, deformation of the tires mostly, internal friction of the parts, stuff like that. But at high speeds, the aero is everything because of that x dot squared term. This also explains why, if you recall the envelope for our decaying oscillator, that it falls off so quickly at the beginning. It's because you're going fast, and that's when the most energy is being taken out. Then as you go slower, the rate at which the energy gets taken out goes proportionately even slower than that. Okay, so now we're going to work at least towards an intuitive definition of the quality factor, and then we'll do a little better job of it later. So the quality factor is just cleverly named Q, and we want it to be big if dE dt is small and vice versa. So in other words, the system will be said to be of high quality if it holds on, if it does a pretty good job of holding on to its energy. It will be of low quality if it doesn't. So let's try to get some sense of how much energy we lose over one cycle. So we remember with great work we got to the position was equal to A times e to the minus gamma t sine of omega damped t plus phi naught. Okay, now what we need is x dot, because we're going to stick that into x dot squared over there. So let's go ahead and calculate that. X dot will be, okay, we'll do the first term, we'll get a minus gamma a e to the minus gamma t times the sine of stuff, omega dt plus phi naught, and then we have to take the derivative of the sine, So we're going to get plus in A, and then when we take the when eventually we take the derivative of what's inside the sign, we're going to pick up an omega d. So then otherwise we're left with e to the minus gamma t. Derivative sign is cosine omega dt plus phi naught. Alrighty. So what do these terms have in common? They both have an a and an e to the minus gamma t in common, so let's group them out. And so we'll say that's minus because intuitively we want to describe it as a dissipation. A e to the minus gamma t, and then we're left with gamma times the sine of stuff, omega dt plus phi naught, minus omega d times the cosine of the same stuff. Okay. Now, if we remember our result here, I'll go ahead and star that for the moment. That means that by star, we get that dE dt is minus cx dot squared. So that gives us minus c, and then when we square things, this minus sign is going to go away. Ca squared. Then we're going to pick up an e to the minus 2 gamma t, then times the stuff in brackets squared. All right. So we want to get some sense of how much energy we lose in one cycle. So we'll go ahead and rewrite this as differentials. So dE will be equal to minus Ca squared e to the minus 2 gamma t times the stuff in brackets squared dt. Okay. Now, we want to do this over a cycle. So loss over a cycle. So it's going to make sense to do a change of variables here. As if we go ahead and look, both the sine and the cosine here go as omega dt plus phi naught. So in one cycle, this is going to increment by 2 pi. So let's go and do a change of variables here. We'll let theta equal the phase, omega dt plus phi naught. Yeah, I know I used theta for something else earlier, but then we made it go away. And so d theta would be equal to omega d dt. So dt is equal to d theta over omega d. All right, so integrating the left-hand side of this guy is just going to give me over the interval delta E, which is what we're trying to find. And for the right-hand side, well, we can pull some constants out, so let's do that. We're going to get a minus Ca squared. When I put in the dt, I'm going to get an over omega d. And everything else depends on t. So we'll have integral 0 to 2 pi d theta. And now I kind of got to lump it and actually take the square, so just bear with me here. So the first term in there is going to give me a gamma squared sine squared. So we'll just say gamma squared sine squared. Now that'll just be of theta because of our change of variables. And then let's see, the cross term, we're going to get a minus 2 gamma omega d times sine theta cosine theta. So minus 2 gamma omega d sine theta cosine theta And then finally we'll have a plus omega d squared cosine squared theta. And like I said, we're going to be integrating all of that from 0 to 2 pi. Well, oops, I lost. My bad. I forgot to insert, and this is kind of a big deal. Oops, there it is. I forgot to insert into here, so I'll just stick it in right there. My e to the minus 2 gamma t, and yeah, I'm just leaving it like that. And here's why I'm going to get away with that. This integral will be insanely hard to do if I have to leave that exponential in there. It's still going to be a little ugly anyway, but it's going to be insanely hard if the exponential's in there. However, if gamma is much less than omega damp, so if it's weak damping, then we can get away with taking this outside the integral because the idea is that it won't have changed very much over that time. So that's what we're going to do. So then delta E will be approximately minus C, minus CA squared over omega D, e to the minus 2 gamma t, and then the integral d theta from 0 to 2 pi of the stuff I just expanded out before. Now for the stuff I expanded out before. When you integrate over a cycle, and this is why we chose one cycle, so keep it right there. So over one cycle, the average value of sine squared of whatever will be equal to the average value of cosine squared of whatever, be equal to a half. And similarly, the average value of the product of sine of whatever and cosine of whatever, as long as it's the same whatever, will be 0. Okie dokie then. So that means we can go back here, and when we're doing this, this sine squared will be a half, doing it over one cycle. I shouldn't be replacing it here because that's what happens after I do the integral. So my integral becomes delta E is approximately, I still have my minus CA squared over omega D e to the minus 2 gamma t. And now after having done the integral, I'll have a I'm sorry, I take it back. I do want to do that substitution. Right, so we will do that substitution. My bad. Momentary brain fart. That becomes a half. That becomes 0. That becomes a half. So now when I'm doing the integral, there we go. There. So now I'm doing the integral. It'll be of 1/2 gamma 1/2 times gamma squared plus omega d squared. There we go. And that's it. Well, all right then. I could just as easily have pulled that out of the integral because that's a constant. So then I'm left with just the integral of 0 to 2 pi d theta, which is 2 pi. All right, so that 2 will cancel the 2 and the half there. And I will be left with minus CA squared over, I'm sorry, minus CA squared times pi over omega d e to the minus 2 gamma t times gamma squared plus omega d squared, which we recognize that that is omega naught squared there. This omega d we'll call the damped period. Here, let me do that with a different color. TD. And we recall from about 1 billion years ago that this C here is equal to 2m gamma. All right, so rearranging that all, I get delta E is minus 2m omega d squared a squared e to the minus 2 gamma t times td. Now, at this point, we can identify our decay constant as being 1 over 2 gamma. So we can rewrite this in a little bit more user-friendly way. This will become a 1/2 ma squared omega naught squared times e to the minus t over tau times td over tau. So this should look kind of familiar from our damped horizontal motion, if you will. This bit here looks kinetic energy-ish, so we'll just say it's like a 1/2 mv squared kind of thing. And this bit here is our damping. The whole bit here corresponds, that much right there, corresponds to the energy. Okay, so what do we get out of this bit right here, the TD over tau? Well, that is going to be we observe that this is the change in energy over the energy itself. So in other words, this is the percentage rate at which we're losing energy. The quality factor Q is defined to be 2 pi over that rate of change, TD over tau. So that becomes omega d, and if we want, we can go ahead and stick 2 gamma back in. Alrighty. So if we go and take a look at this, this does what we want. If we have a slow decay, TD over T will be small, Q will be big. And if we lose energy quickly, TD over tau will be big, and so the quality factor will be low. So that's enough for that for now. We'll be revisiting that when we take a look at forced oscillators. But I figure we should wrap this bit up by taking a look at an example of damped oscillatory motion. Let's go take a look at our friend the pendulum. but this time we'll do it in oil, so we have some viscous drag. So there's our pendulum bob. This time we're in some sort of oil like that. So we'll have 3 forces, but one of them doesn't count. The tension doesn't matter because it's not doing any work. Then we have gravity down, and we have our resistive force up. And it turns out that for the purposes of this problem, the shape of the bob and the viscosity of the oil conspire just right to give us a resistive force equal to 2m times the root of g over L times the speed, which would be L theta dot. All right, so we want to find theta, and theta dot is a function of time, and we're given that our initial angle, theta times 0, is alpha, and we release it from rest, so theta dot at time 0 is 0. All right, so we can write the equation of motion. mx double dot, that can be rewritten as ml theta double dot, will equal, you only need the tangential component of the gravity there, so that will be minus mg sine theta. Then our resistive force will be minus 2m root g over L times L theta dot. Okie dokie. As before, we will pinky swear that our oscillations are small, so that we can avoid incomplete elliptic integrals. So we'll make sine theta approximately theta itself. So that gives us ml, ml theta double dot equals minus mg theta minus 2m root g over L times L theta dot. Well, let's see here. Thank God for small favors. We can go cancel, 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 and we can make that L go away with that L as long as we agree to divide by that L. Okay, so we can go ahead and put this into standard form. We have theta double dot equals theta double dot plus 2 root g over L theta dot plus g over L theta equals 0. So if we look at this, we recognize that the radical here is gamma, and that guy right there is omega naught squared. So that means gamma squared equals omega naught squared, which means it's critically damped. Since it's critically damped, we've got to pull out our special solution with the extra kernel. So that'll be theta of t is equal to at plus b e to the minus gamma t. So as before, a has to equal gamma b. We can, and so let's see, we will so set alpha equal to theta at time 0. Well, times 0, that bit is 0, so this is just going to be b times e to the minus gamma t, right? And t itself will be 0, so that just becomes 1, so that means that b is equal to alpha, therefore a is equal to gamma. alpha. So our theta as a function of time becomes alpha times gamma t plus 1 e to the minus gamma t. Putting in what those tidbits are, that's going to be alpha times the square root of g over L times t plus 1 e to the minus root g over L times t. All right. And then to get theta dot as a function of time, we just go ahead and differentiate that. So differentiating the first term is just going to give me an alpha gamma e to the minus gamma t. Differentiating the second term is going to bring down a minus gamma, so we'll have a minus alpha gamma times gamma t plus 1 times e to the minus gamma t. Alrighty, well, for what it's worth, this guy here is going to cancel that term there. And so I'm left with that gamma, there's going to become gamma squared. Oops. Right there. So that's just going to be g over L. So we're going to get minus alpha g over L times t e to the minus root g over L times t. So if we take a look at this, what's going to happen is at first the linear part's going to dominate here, so we'll have the bob speeding up quickly, and then as the exponential kicks in, we'll start slowing down as we asymptotically return to the equilibrium position. Okay, next time we're going to continue our foray into oscillations, and we're going to take a look at what happens if we start forcing the oscillator.